Okay, so let's start with the second talk of our morning session. It's a pleasure for me to introduce to you Dr. Jiakang Bao from the University of Tokyo and currently at JMU, and he's going to talk to us about Quiver Algebras from crystals. Please go ahead, Jiakang.
Thank you. Thanks for inviting me here to give a talk. So I'll talk about Quiver algebras from crystals. So Seba has already given a very nice talk on the crystals, so I'll construct some Quiver algebras for these crystals and quivers. So for Yannian algebras, we know there is this elliptic trigonometric rational hierarchy like this. And for Quiver BPS algebras arise from discounting D-brane bound states, we also expect this hierarchy like elliptic Quiver BPS algebras or elliptic quantum tree algebras. Also, if you include like chiral quivers and Quiver Yannians. So the input data will just be quivers and their superpotentials. So for Calabi-Yau threefolds, thanks to like these authors and others, we have a series of papers telling us how to construct the quivers and superpotential from the Calabi-Yau threefolds. Well, the round nodes are the gauge nodes, square nodes are the flavor nodes, and arrows are chiral multiplets. And this counting problem can be combinatorially described by the crystal melting models. So, this provides a way to construct the so-called Quiver BPS algebras. So in Willie and Masahito's paper, they build this algebra from, because you would expect these crystals to be a representation. And in Dima Galahov and Masahito's paper, they derived it in using supersymmetric quantum mechanics, and later in Galahov Yamazaki, they just introduced like this Quiver BPS algebras for this hierarchy, and also in Go and Watanabe's paper, they discussed this quantum toroid algebra case. So there are some natural questions like what about Calabi-Yau fourfolds, and what about like more general cases like the non-toric quivers. So first I will talk about the construction of Quiver BPS algebras and also some different type of algebras which we call double Quiver algebras and their crystal representations from the JK residues, which is based on a work with Masahito. And also, if time permits, I will talk about the Quiver BPS algebras of the DE types because they violate some of one of the conditions we need to construct to construct the crystal representations of these algebras, and this is some ongoing work. So, right. So we want to compute the partition function either for 4 supercharges or 2 supercharges, and we know this. We have this Jeffrey-Kuhlmann residue formula, and Go also introduced used this JK residue formula yesterday. So you probably know this way better than I do. So I'll just go through the formula and list the expressions just for completeness, and because we are going to use some of the factors, ingredients there. So this is the formula, and for the quivers, we are going to focus on those only with unitary groups, and the methods are bifundamentals of the joints, and the superpotentials are polynomials of these fields. So UI would be the fugacities or chemical potentials, if you like, for the gauge nodes, and epsilons would be those for the flavors. So this is the one-loop determinant, which is like the integrand, and then for 2 SUSY and 4 SUSY cases, we have like these expressions, which have contributions from these multiplets. Right. So these are the expressions. The basic idea is that when you have a denominator, they would contribute, or they would correspond to like the atoms in the crystals, and the numerators would just do the job to cancel some of the extra poles to form this structure of the crystal. And this zeta, well, depending on like the different cases, but it's an odd function. Right, so the factors in the denominator would give these hyperplanes of this form, where this Qi of U, here U is a like vector U1, U2, up to say un, and qi would be the covector. So it's basically the coefficients in front of the u's. So this qi of u is just say u1 minus u2 or u2 minus u3, something like this. And this is why, and this is a consequence of considering only the bifundamentals and the joints. So it's always of form like ui minus uj. And these dots are these epsilons coming from the weights of the edges. And let's say we just denote the union of these hyperplanes as M singular, and the set of isolated points where at least n linearly independent hyperplanes meet would be denoted as M singular star. And in the JK residue formula, we know there is this covector eta, which needs to satisfy this condition to give a non-trivial result. So it has to be living in the cone spanned by these qi, where so the coefficients aj are positive or non-negative. And we shall mainly focus on the 1-1-1 case, and we'll briefly comment on more general eta. So this is the JK residue formula. You just take the determinant of this qi, and we say it's admissible. So it will give non-zero results if eta is in the cone, and otherwise we say it's inadmissible. And there's an equivalent constructive definition, which basically says that the JK residue can be written as like an iterated residues. So taking the JK residue is like taking a sequence of residues. I mean, we're not going to go into the like details and calculations, but we just need to have this idea in mind. So yeah, right. So the poles would just correspond to the atoms in the crystal, and taking the residues would correspond to like adding atoms to a crystal state, like this. And because here we have like two different ways to reach this configuration, and this like the history or the order of adding these atoms is kind of forgotten or taken care by the factor of the from the Weyl group. Right. So for the crystals, once we know the quivers from the toric Calabi-Yau threefolds, we can construct the crystals thanks to these authors, and also for Calabi-Yau fourfolds, we know how to construct the quivers thanks to these papers, and also Seba also discussed like how you can construct the 40 crystals. So I can just go through the crystals very quickly, but I just want to set up some notations, because sometimes we use like different names like crystals, molten crystals, etc. And I just want to assign every name for something specific to make our discussion easier. And also for generic quiver, the idea is very similar. So you can basically carry what you learned from the previous talk, have this idea in mind, and just a little bit modifications in some parts like the Jacobi algebra. But anyway, the poles give the non-trivial residues. They are in one-to-one correspondence with the atoms in the crystals. So we can actually show this, that these non-trivial poles, they would give us like the structure of the crystals. And likewise, we can do the similar thing for generic quivers, because we are still using the JK residues. So suppose we have the dimension vector for your gauge nodes, which is n, and let's say this u equal to u star, which gives a non-trivial JK residue, and we denote the set of these u's as this fractal u, and also the set of hyperplanes that's meet at this u star would be known as denoted as this fractal h. And then of course the hyperplanes are of this form, say uj minus ui, and ab are they correspond different nodes. Then this actually gives us a system of linear equations, and the solution will be this u star, and this in this u star solution, all these ui a star would be a linear combination of the equivalence parameters epsilon k, and we just collect this u I a star and call it like a of u star, And also the set of atoms at level n is just the union of U star coming with this dimension vector n. And we say if this usual n is just the sum of Na equal to n. And then the full set of atoms is just, you just take the union of all these A's at ON. And well, because of this obvious inclusion, so it's actually a direct system, so we can just write it as a direct limit. And then the crystal is just defined as a weighted graph with the vertices given by the atoms, and the edges are given, they come from the arrows or edges in the quiver. So we say there's an edge from A to B, atom A to atom B, if there is a hyperplane of this form, which is like UA minus UB, and the weight is given by the difference of the atoms. So and we say like these edges are the chemical bonds. So the condition we need is this so-called the no overlap condition, because, well, if you like, this A, well, you can think of this as a multiset, because you can have say UIA and UJB, they are equal, so you have like say the same solution, but we require them, all of these like UIA star, UJB star, we require them not to be equal, and we say this is if they are, none of these are equal, we say it satisfies the no overlap condition. Well, because in terms of the crystals, this means like the atoms do not occupy the same position, so they do not overlap. So this is the condition we need to well, for the crystal and also to construct the algebras. Yeah, so this is basically what I just said. And in terms of the JQ residue formula, this means that we only consider simple poles, because for high order poles, there could be some issues, as we mentioned. And this is exactly the case, namely the DFND type cases, they would violate the no overlap condition. So that's why we would like to discuss like these DE types separately. So let's just say, well, just to make the discussion easier, let's just say like if the crystal is like this full thing, and the molecule would be like a finite subgraph, satisfying this like melting rule, and we also see this in the previous talk. So right, and also we say if it's the molecule comes from a non-trivial JQ residue as a crystal state, because most of the time we're going to talk about eta 1111, but for more general eta, it could be possible that at a single step, one needs to add multiple atoms like simultaneously, because it could be possible that eta n at level n does not live in the cone, but at the next level n plus 1, it will be live in the cone spanned by h1 up to hn and hn plus 1. So in other words, you cannot just add a single A, because the JQ residue just vanishes, so you have to add 2 of them. So also in this paper, where the authors studied like the conifold case, they call these like glasses and polymers, so because you have to add like multiple atoms, so it's like polymer. And also for molten crystal, we just save this name for the complement, because we can consider this space given by this all the atoms in the molten crystal. So in the usual torque case, we know that the Jacobi algebra, which is the path algebra quotiented by the relations, has this as a module. So in the path algebra, we just have the elements as these paths, and their products are given by the concatenations of the path. So if it's 0 if they cannot be concatenated. So for at least for 1111 in the torque case, well, this is a module where an arrow acts on the atom, so it takes you to the next atom it's connected to, and this can be extended linearly on the whole M. But for non-torque cases, the relation can be more general. In other words, in torque cases, usually we have like say P1 minus P2 equal to 0, and the relation is just P1 equal to P2. Namely, you have say 2 paths given by P1 and P2, they would have the same endpoint. But well, for a generic quiver, this may not be the case. It could be like a P1, like A1 P1 plus up to A and Pn equal to 0. But the JK residues, the poles, they do not see this relation. What they see is this relation. So actually, we still have a sort of path, multiple paths, P1, P2 up to Pn, and they should end at the same point. So this is the sort of like new or modified Jacobi algebra, such that the molten crystal would be a module of this CQ quotient by this like enhanced relations. Right. So now we like to, after setting up the terminologies, having the crystals, we like to construct the algebras which have these crystals as their representations. And we know for toric Calabi-Yau threefolds, these are the Quiver BPS algebras. Right, at least for those satisfying the no overlap condition. And this is the relations of the algebras in terms of the currents. Of course, we have this like expansions or modal expansions of the currents giving us the generators, but I'm not gonna write these expansions here because we are mainly gonna work on with these currents. In particular, I have this like formal delta function, which is just 1 over z in the rational case, and the sum of z to the power n for all integer n in trigonometric and elliptic case. Right, and so the key factor, as we can see, basically for every relation like psi e, psi f, e, f, we have this factor phi, which is called the bond factor. So it looks like this. The numerator has all, so given like a and b, the numerator contains all the arrows from A to B, and the denominator contains all the arrows from B to A. So we have these corresponding factors. And for non-symmetric quivers, which in the trigonometric and elliptic cases, when you take the expansion of the currents, there could be like fractional powers. So this is like the balanced version of the bond factor to take care of these fractional powers. But we're mainly going to focus on this bond factor because there's always something you can do to balance it. Right. So we're just going to, because there are some extra central elements, but in our discussions, we're going to take it to be trivial. And in this case, we have the crystal states as the representation given by this, where the function called the charge function is a product of the bond factor we've just seen, and these are like so for each atom appearing in the crystal states, we have such a bond factor for like each atom B for this A, and this sharp side comes from the framing, so it's basically the same as the bond factors, but depends on what framing you use. So first, the crystal states are eigenstates of like these psi, of you like some Cartan type currents, and these currents they would add atoms to the crystals, like the sort of creation operator, and F does the opposite job and removes the atoms, so it's like the annihilation operator. And the key factor is that the poles of the charge function, they are precisely the addable and removable atoms in the crystal state. So can we see this from the JK residue formula? Because I started with like this using this to compute the partition function. So the trick is to first remove the vector multiplets, because one can show that the vector multiplets, they never contribute non-trivial poles, because the factors in the denominator, they always get canceled. But also we also remove like the ones from the numerator. So, and then we only keep the chiral multiplets, but we keep half of them and take this epsilon, which is the sum of all the epsilon cases, to be 0. So for the factor from A to B, we just keep the numerator, and for the factors from B to A, we just keep the denominator. And well, it's obvious that when we just keep like half from each part, we recover the bond factor. And I just mentioned that when we can use the J.K. residue formula, like the poles, to show that they precisely correspond to the atoms in the crystals. And now, if we just keep like these sort of half of the factors, the expression would exactly giving us the addable and removable atoms. Namely, this would recover the charge function psi we just see. But what about those with two supercharges? The thing is, it's very hard to find a charge function whose poles would give us precisely the addable and removable atoms. Well, firstly, I mean, okay, we know the trick that from the J.K. residue formula for theories with four supercharges, we can keep half of them. But here, for two supercharges, we don't know, like, there is no such like clear thing that to tell us like what kind of half we can keep, because things do not come in pairs. And actually, if you really want a charge function that gives the poles of the addable and removable atoms, it's possible, but it would be state dependent. In other words, if you want to cook up some algebraic relations independent of the states, it's very hard. It does not seem to be possible. So in Galohov and Lee's paper, they just showed this for the C4 case, which we know is the solid partition. And now the charge function looks like this. So the exact expressions of these like phi 1, phi 4, phi 5 are not important, but we just want to show that they are state dependent. So for each phi 1, well, first this hash psi, it's fine. It's from the framing, it's okay. And this phi 1, it's still from the each single atom, so it's fine. But then you want this phi 4k. So for each configuration that looks like this, you need something called phi 4k, which is like several factors with different k. And then if you have a row of 5 boxes, you need some extra factor, which is called phi 5. So it's well, I guess it's not possible to cook up some independent algebraic relations if you just want to use this charge function, although it does contain all the addable and removable atoms and does not have any extra things. So let's just keep all the factors, because before we keep half of them. Now let's just keep like all the factors, which basically looks like this. This is like the new charge function, and then which we call psi tilde, and this is like the new bound factor, which we call phi tilde. So it's basically keeping everything from the residue formula. And let's make an ansatz saying like, okay, these are the currents we want analogous to the Quiver BPS algebra case with this psi tilde as the charge function. But there is one caveat, that because now, well, first, I mean, psi tilde only have addable poles, because so not like addable and removable poles. So in F we need to use like C minus A rather than C. But more importantly, the whole like if we keep all the factors from the integrand, namely we use psi tilde, there would be extra poles, because I mean there can be some poles inadmissible due to this eta. So we just collect them all together, and using this some new omega tilde currents, and just put them together. Say, okay, if you are not admissible, then you go to this omega tilde. And indeed, we can find that if we check, like, so we apply E first to the crystal state, then apply a different E current to the crystal state, and then we just swap the order, check the other E acting on say the crystal state, and likewise we apply psi on the crystal state, then apply E, or we do it in the other way, apply E first and then apply psi. We can see if these coefficients would give us something independent of the crystal states, and indeed we have something like this, which is which give us the relations of this new algebras, which we call the double quiver algebras, and it's double because in the quiver BPS algebras we keep like half of the factors, and now we keep the full factors, so it's sort of double. So there's So for example, in this psi E relation, you can see there is this d tilde and d tilde on both sides, but this is not redundant. Well, first d tilde is like this, and it's not redundant because when you take the currents, the mode expansions of the currents, I mean, with or without these factors, you would have different mode relations. And also it's important when you want to say sort of bootstrap or cook up the relations from the crystals when you add atoms at some sort of like non-generic positions. But anyway, this is the algebras, and the coefficients, which is given by like the residues of the psi tilde charge function, they also encode these non-trivial coefficients in the partition functions. So for theories with four supercharges, we know the double quiver algebras. Well, as we can see, it's not the quiver BPC algebra, but we can slightly enlarge the double quiver algebras by introducing some sort of square roots of the psi tilde, regardless of what that means. But if we just include this, like slightly enlarge the double quiver BPC algebras with these currents, like the square roots of this psi tilde, we can actually show that the quiver BPC algebra is a subalgebra.
You mean that your answers for the function phi
Yes.
is that combination of
Right.
pieces from the integral?
Right.
Okay.
Right. So yeah. So what about those that do not satisfy the no overlap conditions? So let's just consider the quantum toroidal algebras of DE types. Because the coproduct structure is much simpler compared to the rational version. And well, it's possible that there are still quiver BPC algebras in the sense that we have the crystals as well, some sort of crystals from the algebras. So these are the other DE types quivers, and now the bifundamentals would have weights q to the q to the -1, and these adjoints would have weights q squared. And the JK residue formula does not seem to give the right result, which was obtained in these two papers, basically using Nagao-Nakajima's method, and in particular, well, for example, in Nekrasov's paper on BPSFT correspondence, in one of the papers, he also computed the QQ character for the default case, and there were some extra contributions from the non-isolated fixed loci. So that's something we don't see from somehow we don't see from the formula. And also, if we just, well, for mathematicians, I mean, we know for the A-type cases, there is a standard way to construct the Fock modules, namely the Young diagrams from the vector representations, which is a column or a row of boxes using the coproduct structure. But it turns out if you want to apply this to the D types, the Fock module is not well defined. And also there were some sort of, if you just want to say, okay, let's forget about the algebras and just look at what kind of like combinatorial structure we have from these modules, and you do the counting, like count the boxes or atoms. It turns out that it coincides with the results from the JK residue formula, but not the ones from these papers. So this is the actual partition function. Somehow it can be factorized into two parts, and this part is the thing you get from the JK residue formula, or you get from these kind of analogous, like generalized Young diagrams, which you're going to see. So I've also asked like experts on this, and they're not aware of any sort of like factorization, maybe separating the isolated fixed points. But somehow this is something we can check, like sort of at least perturbatively. Right, so you can see, well, these are the like Fock modules or expected Fock modules, and you can see the decrease of the quality of the figures because, we haven't finalized everything. But anyway, this is for the D-type case, and this is like E6, E6, E7, E8. So it's, well, the D-type is, I guess it's most clear because you can see from each column, you can have 0, 1, which are and 2, and then you have a sequence up to m-2, and then you have a bifurcation m-1 and n, then you go back to m-2. This is like exactly how the d-type like affine thinking diagram looks like. And here we have this delta H equal to 1. This means that the column on the right has the highest, the highest atom in a column on the right has to be lower than the column on its left by 1. So for example, if we have say if we want to have say like a 2 in the second column, then we need to have 3 in the first column. So in the A-type case, we know it's just Young diagram. So delta H is 0, and here somehow delta H should be 1. And likewise, it's more complicated. But again, these columns are the things you can construct from the E-type thinking diagrams, and you have different delta H. And also there were some shaded boxes. These are called so for the other boxes, like they are the usual like boxes you can add or grow in the positive direction. But for a vector representation, just like in the A-type case, you can also grow things in the negative direction. So these shaded ones, they would correspond to the negative directions. And also when we construct the Fock module or the McMahon module, we don't want these negative things. Right, okay. Yeah, so I started a bit late, so I can have like 5 more minutes. Right, so let's just use the D-type case as an example to see what actually goes wrong when we construct the Fock module using the vector representation. So this is the vector representation, which works for A, D, E, and also you can do this for B, C, F, G as well. Then, this HA here is the height of the unique addable or removable atom or box of color A if it exists. And here you have some different psi, which is a function, looks like this. And we know there is this coproduct, so we can just use this to cook up the Fock module just by adding more columns. And because we have this condition delta H equal to 1, namely the left column should always be higher than its right column. So when we apply the coproduct, the first part is okay, but in the second part we have EA acting on the second column, so you cannot reach the height of its left neighbor. So this puts constraints on the coefficient, and because of this formal delta function, when HA of y1 and HA of y2, they're equal, we need the coefficient to be 0, and this gives us the result that the spectral parameter or this parameter on the second column U prime should be equal to U to the Q minus 2, which is, this minus 2 or this 2 is basically like the diagonal 2 in the Cartan, or like the adjoint weight. But then if you look at this configuration, and I want to add this blue 2 to the box, which is still valid, but now again I use the coproduct and check the second part, EA acting on this y2. Now I have something similar as a coefficient, and now I know like HA of y1 is HA of y2 plus 2, but and we have this U prime equal to U to the Q minus 2, and plugging this, it turns out that this denominator will be 0. So it's not well defined. And recently, Jinbo Muhin, they had a paper called combinatorial basis, blah blah, for the affine, for the combinatorial algebra of GL2, and this is basically their combinatorial basis. Is basically what we just saw for the actions of the Quiver-Yannians or Quiver-BPS algebras with this charge function psi built from these bound factors. And now we can use now for the crystal representations for the D types, what we want is the factor common framing. First we have a factor for the zeros, zeroth atom, which is the starting point, and then we also need something for the box or atom of corresponding node 1, which is the one next to it. Well, because first, I mean, if I want to start to grow this Fock module crystal, I need to have something to trigger my the zeroth atom here, and also if I want to have for this one to go into the negative direction, I also need this one here. But anyway, these are the factors, sort of bound factors from the framing. However, the problem is that you would have higher order poles. So this is exactly when you have higher order poles. Namely, if I want this two and this blue two, they would have the same coordinates in terms parameterized by u and q's. So this is the place when you have higher order poles, and because here it's a second order pole because I have two of these. But if you have more columns and you go higher, of course you can have higher order poles of any order. So there are several approaches we can do, at least to construct some Fock or McMahon type modules. First, we set this to be 0, this to be phi 0 to be 1. Namely, we just remove this thing. But in this phi 1, the framing this z minus u starts to add boxes or atoms to the negative directions, and this thing here in the numerator. This is there because in the vector representation, we just want one column, so we don't want to have this extra one here in the second column. So this cancels the pole here. So now, if we just remove this, in other words, we're having like some sort of Fock module not in the xy plane, but in the xz plane, and because of this z minus u, it will have a long tail in your first column, because just as in the vector representation. So we say it's like tailed Fock module. And also, okay, I still want, say, if I still want this Fock module, or what people call the Young wall, analogous to the Young diagram, then I can just remove the denominator of this. But then this is not homogeneous, so we say, okay, maybe we can consider like the shifted quantum Quiver algebras, where you have, well, here you have like, because in the psi, in the occurrence of psi, the expansion starts from say psi 0, psi 1, but now you have like psi minus 1 as well. And also use some topological coproduct, but not the usual, not the coproducts we just saw before, but it's twisted by some anti-evolution, because this new coproduct will be well defined, not just for integral modules, but also any highest width modules. But these two approaches do not really solve the problem that of the higher order poles. We're just trying to avoid the higher order poles. So the actual way is to use the derivatives of the formal delta function, and then your psi currents, which where the crystal states were eigenstates of these psi currents, but now these psi currents would act non-diagonally. And in fact, this was also encountered in the PT counting in these two papers, as Go mentioned yesterday. So in the PT counting, you can have like, say, pole of order 2 for PT3 and a pole of order 3 in PT4, but now you can have like any order poles, so you need like all orders of derivatives of the delta function. Yeah.
Purely from the representation theory viewpoint.
Yes.
First of all, does the Fock module exist, or like?
So for the quantum of algebra, people have constructed at least for the D-type case. So and that's what people expect. That's okay, maybe. So at least we should have something like.
So it exists as a representation. I mean,
well, for the
is it?
We don't know actually. So for the quantum, that's why I was saying okay.
No, sorry, but I mean, yeah. I mean, if Fock module is defined in a canonical way, so it either exists or it doesn't exist, right? So which of the options is true?
We expect the Fock module looks like this. But somehow it's just not. Yeah, there were some issues.
Okay, so then it sounds like a standard definition of fork module doesn't work.
Right.
That's what you say. I see.
Right.
And then you're trying to construct some modules, and but then you mentioned three different possibilities.
So this is
what-
the ultimate one we want. But I haven't, because we haven't written down, like, there are some coefficient, or if you like, constant factors, prefactors we haven't fixed.
Oh, I see. So it's not like there are three different representations, but
Right,
you're trying to construct the three.
Okay, this is also representation, but it's not the standard, in the standard like sense, because there is like a long tail in the negative direction. So it's something like which, okay, let's try to avoid the higher pole, and then we cannot go into this direction, then we'll go this direction. But then there is something we cannot remove in the negative direction. So then okay, you like still some sort of module, but it's not the one we really want. And this one is like the shifted one.
Okay, so you mean do you still get the three different representations for that?
In some sense, yes, but this is like shifted, not the one
Yeah.
without shift. And if we really want to make the thing says we're posing the question, then we really need to use this.
Okay.
Man, I don't have the expression here, but yeah.
What if you just take the affine thinking Quiver and take framing one at the affine node and then run the.
Oh, that's possible. Yeah, but I want to have the framing just one single framing to control.
Yeah.
But I can change framing. Yeah.
Then just apply the mathematical plus result to that across and take case of that.
You mean difference framing?
Right.
You mean change the framing, not that one. Not
I
like
just take the one framing measure one
Mhm.
affine node 0 else
Uh-huh.
and take the B1 case of that and apply mathematical result that one for the algebras. So say
Mhm.
affine thinking Quiver acts on the B1 case of that and what is that the will that give you the right result?
I don't think it will work. I don't think it will work. I guess it will have something similar if you just choose a different final.
Is it the same framing as yours? You also have one somewhere, but
No, if you change it, you would still have something probably similar. But we can discuss later. I don't think it. Yeah, I'm not sure, but I doubt it. It wouldn't. Yeah, I don't think it would. Okay. Right. Yeah. Okay. But anyway, right. So for the algebras, we use we talk about the algebras for the cyclic chambers, namely eta 111. What about the representations like the algebras for like the non-cyclic chambers? And also, can we incorporate for these non-trivial coefficients, like especially for in the fourfold case, or if you like the DT4 counting? Maybe if we put them into the states, we can have some new algebras. So then this is a question like what qualifies as a BPS algebra, because we don't know the properties of the double quiver algebras or maybe there are some potential new algebras like the coproduct or the connection to integrability or those not yet known VOAs. And maybe also, as Seba talked about cluster algebras, I mean, we would expect that the algebras should be isomorphic in the subdualities or maybe trialities, but even for those Calabi-Yau threefolds, we only know a small family that they are isomorphic. And recently there is some proof extending this to the F0 quiver or if you like KP2 quiver, but they also need to introduce some sort of square root of the psi current. And also maybe connections to like the quiver W algebras and also QQ characters. I mean, it's natural to believe that they are like they are talking about talking about the same story, but in different languages, but we don't know like how exactly we can connect them. And also there are, so this is like the crystal formalism and there's some, I call it gluing formalism here because I want to emphasize that it's gluing, but they do call it vertex formalisms in this paper for DT4 counting and also in the cross of Piazzalonga, they call it like 4G network. And in fact, at least just if we just look at the expressions, these two gluing, they do not look exactly the same. So now we have like at least like three things. So how to identify these things will also be an interesting question. Yeah, so I guess I will stop here. All right, thank you.
Thank you, Jiakang, for the talk. Any questions? Yes.
You mentioned in DT case, sorry, DE case, JK residue fail recovering the mathematician's result. Do you have any physics explanation to understand why?
Basically, it's like you have some extra non-isolated fixed points, but I don't know why the JK residue doesn't work.
I mean, previously there's such an example, but people identified it's because of fine tuning of the spot potential, or there's like a direction issue.
Necrostal computer QQ character shows that there were some extra contributions. Not exactly this partition function, but if you apply the JK residue formula to do this thing, yeah, it looks like there was something missing. But I going through like the steps of like getting the localization, I don't see where it goes wrong. So this part I'm still not sure.
Any other questions? Yes, Pietro.
So mentioned some papers by Wei, also I include papers Masakito about Quiver Algebras. So could you clarify how that relates to your presentation?
Right. The BPS algebras, they are like sort of more standard construction and for like Calabi-Yau three-folds. But now here we have like we want to sort of do this for like four-folds as well. So it's if you have, they are not the same, of course. But then if you enlarge this like the double algebras with some extra thing, you can see that the Quiver BPS algebra is a subalgebra of that. But again, I'm not calling this the like double Quiver BPS algebra because, as you said, there were many properties we don't know as we would expect for something like a BPS algebra. So just it's a Quiver algebra or double Quiver algebra. I'm not calling it like a BPS algebra.
Yeah, so the Quiver BPS algebra itself is defined for any Quiver abstractly that is the potential. So what we thought originally is that we can take exactly the same algebra and then try to adapt that to the Calabi-Yau case if it's out of the crystal. That's a natural thing to do. But in general, that doesn't seem to work. There are some, and then I almost gave up. But then I realized that we can change the algebra itself, change the definition of the algebra, somewhat enlarge the algebra, and then it can adopt the more general situation, including Calabi-Yau or more general theory. Of course, then you have a different algebra from the original Yang. So that makes the situation a little bit complicated, but at least these two are not completely unrelated here. Maybe it's something larger, so that's the story.
Any other questions? Yes.
Question one. Does the character of the vacuum model for this Quiver algebra will reproduce the genetic function of the?
Yeah, it should be, yeah, because you have this representation, just do the counting.
And is there some similar relation, like the cell relation?
Oh yeah, that's right. I've been trying to avoid this third relations. So I'm not showing anything.
Yeah.
But we're not. Yeah, we have not considered like if there were third type relations here. So I've been always avoiding these kind of the extra relations. But yeah, it could be. But we can.
Any other questions? If not, let's thank Jiakang again.